Okay, so this is part 2 of our revision for forces in motion. I was rather rudely cut off last time because I didn't realise this free software only does videos of maximum 15 minutes, but actually it's probably a good idea to chop it into. Okay, so we got as far as looking at Newton's laws of motion. Okay, so this is the first law. You won't have to write this down in an exam, but you do need to understand what it means. So if there is no resultant force acting on an object, so that means there are either no forces or the forces are balanced and they cancel each other out. An object will either stay at rest or move with constant velocity. So that's the thing that's quite difficult for most people to understand. Most people think you need a force for something to move. So let's look at an example of how we can have constant velocity without a force. So this first law was really, first discovered really by Galileo. And he did a thought experiment. Most of the best physicists did thought experiments. Einstein was very famous for this. And he imagined a marble, so you know, like a glass marble, very smooth, in a very smooth bowl. So when a physicist says very smooth, we imagine there's no friction. Of course, that's impossible in reality, but let's just imagine that there was no friction on this bowl. And he asked the question, okay, if we let go of this ball, how far up the other side will it roll? Well, we know, just thinking about energy, that it can only go to the same height. So the ball has gravitational energy, it accelerates, it gets faster, so the gravitational energy turns into kinetic energy, and then of course when it rolls up the other side, the kinetic energy turns back into gravitational. If there's no friction, there's no energy lost through heat, so it will finish with the same amount of gravitational energy that it started with. Okay, that's fine. So Galileo said, well, what if we have a longer bowl? And I hope fairly self-evidently the same happens, because we didn't specify how long the bowl was there. It's just a longer bowl, the same thing will happen. Now, of course, once it's rolling across the bottom, it's not going to get any faster. So it rolls with constant velocity across the bottom there. It's got kinetic energy, but it's not losing any energy because there's no friction. And then it rolls up the other side. So, of course, Galileo's stroke of genius was to say, well, what if the bowl never ends? And, of course, if it never meets the other side, then the ball moves with constant velocity. So there are no resultant forces on that ball. It's moving with constant velocity. So that's where that second part of the Newton's laws comes from. Now, obviously, it's not often in everyday life we have no friction, but let's have a look where there is an example of friction. So if you imagine I'm cycling to work. This has happened, not here in Qatar, but in the distant past. Okay, at constant velocity. So if I think about the forces on me, obviously I'm pushing on the pedals, there's a pushing force. But there is also friction. This is the real world. There's quite considerable friction. And when I'm traveling at constant velocity, the pushing force is equal to the friction. I.e., if we add those forces together, they cancel each other out. There is no resultant force. Similar example is if we look at terminal velocity. You know, if we drop a dog out of an aeroplane, as soon as the dog falls out, there's really only one force on the dog, that's gravity pulling down, so the dog accelerates. But of course, as the dog goes faster, air resistance, the friction in the opposite direction, gets bigger and bigger and bigger. So the dog still accelerates, but the rate of acceleration is not quite as much. So it won't be 10 meters per second squared. It'll get less and less until the air resistance is equal to the force of gravity. So there is now no resultant force on the dog. The dog moves at constant speed. And we call that constant speed or that constant velocity the terminal velocity. So that applies to falling objects. And of course the dog will continue to fall at constant velocity, at the terminal velocity, until it hits the ground. Okay, so that's the first law. And the first law deals with when there's no resultant forces or no forces. And the second law look at what happens when there is a force. And I hope fairly self-evidently that if the forces are unbalanced, so if I push harder, I will go faster. I will accelerate. My velocity changes. And in fact, the definition of acceleration is the rate of change of velocity, how much the velocity changes per second. And that takes us back to that formula we looked at before, the change in velocity divided by the time. Of course, if I stop pedaling, okay, again, there is a resultant force. Of course, this time I will decelerate, I will slow down. Okay, so if the resultant force, an object accelerates, it changes its velocity. And Newton discovered, of course, that there was a connection between the force and the acceleration. The bigger the force, the bigger the acceleration. And the constant there, the constant of proportionality, we say in mathematics, is the mass of the object. So this is Newton's second law. It's actually a mathematical relationship between the resultant force, that's the force you get when you've added all the forces together, and the acceleration. So let's have a look at an example. So here we have, I'm pushing on my bike with a force of 100 newtons. The force of friction is 60 newtons, so my pushing force is bigger. I'm going to accelerate. And the mass of me and my bike is 100 kilograms. And the question says, what is the acceleration? Well, first of all, we've got to find out what is that resultant force. So I'm pushing forwards with a force of 100 newtons. The force of friction against me is 60, so my resultant force is 40 newtons in the direction that I'm moving. Okay, as usual, we write the formula down. Resultant force equals mass times acceleration. We put the numbers in. We've just found that the resultant force is 40 newtons. We know the mass of myself and the bicycle is 100 kilograms. We want to find out what the acceleration is, A. Okay, well, we do the same thing to both sides. We're going to divide both sides by 100. 40 divided by 100 is 0.4. 100A divided by 100 is just A. So we get our answer. My acceleration will be 0.4 meters per second, which we write as meters per second squared. Okay, we did a little bit then on gravity when we were doing this project. Do you remember we discovered that gravity is a force between all objects? Many people just think of gravity as the force attraction to the Earth, but that is not true. Everything in your house is attracted to each other. But it's a very, very small force, gravity. In nuclear reactions, we tend to ignore it because it's so small. There's an example. If I calculate the force of attraction between myself and Mrs. Porter, we stood on the Empire State Building there quite a few years ago, a metre apart, and the force of attraction between us is 0.000004 newtons, less than a millionth of a newton. So we don't notice that in everyday life. We only notice the force of gravity when one or both of the objects is really big, like a planet or a moon. Okay, so the force of gravity does depend on the size of the objects. The bigger the objects, the bigger the force of gravity, but also the distance apart. The further apart they are, the smaller the force. Okay, now the force of gravity, remember, has a special name. We call it weight. And because it's a force, it is measured in newtons. So this is a common mistake to non-physicists, saying, oh, I weigh 80 kilograms. Well, you don't. Your weight is in newtons. On the Earth, my weight is a bit more than this now, but let's imagine it's 800 newtons. If I go on the Moon, my weight is only about 130 newtons. And quite evidently from those pictures, it's because the Moon is smaller, so the force of attraction between you and the Moon is smaller. And of course, if you're floating in deep space a long way away from any of the planets, so the force of gravity between you and the planets is very small, you are weightless. Okay. So that is weight, the force of gravity. Mass is a measure of the amount of material you're made from, the atoms, the molecules, whatever. And that is measured in kilograms. Okay, so I have a mass, or used to have a mass of about 80 kilograms. If I go to the Moon, well, I'm made of the same amount of stuff, the same number of atoms, the same type of atoms and molecules. My mass is the same. And I'm floating in deep space, my mass is 80 kilograms. Okay, so mass measures the amount of material you measure from, it's measured in kilograms. It doesn't change in different gravitational fields. Weight is the force of gravity, it's measured in newtons. That does change depending where you are. Now, of course, there is a connection between the two. And that connection is the gravitational field strength. So the stronger the gravitational field strength, the bigger the force of gravity, the bigger the weight. And we've got a little formula we have to learn. We've been using this in our last topic as well, that weight is mass times gravitational field strength. Now, on the Earth, the gravitational field strength is around 10. We normally take it in 10 in IGCSE. In IB, you'll use 9.81. But it actually depends where on the Earth you are. There's a very slight difference in the gravitational field strength depending where you are on the Earth. So we normally approximate it to 10. Okay, so very simply, on the Earth, my mass is 80 kilograms. The gravitational field strength on the Earth is around 10 newtons per kilogram. So my weight is 800 newtons. Okay, two more bits of this topic to go. We look at stopping distances. Okay, so this is the distance it takes a car or any item of transport to stop. Okay, now the stopping distance is in two parts normally. The thinking distance. So this is the time it takes the person driving the car to realise they need to stop and to put the brake down. So that's like the reaction distance. Okay, although we're talking about a time. So it's related to the reaction time. Yeah, the distance it takes the driver to react. And of course, that's affected by the mental state of the driver. If the driver is tired, if the driver has been drinking alcohol, or under the influence of other drugs. Now, the braking distance, actually, and it also depends on the speed, because of course, if the car's going faster, that distance it travels while thinking is going to be more, isn't it? And then we've got the braking distance. So this is the distance the car goes once the brakes have been applied. In English, we say that we've applied the brakes, or put the brakes on. And of course, that depends on how fast you're going again. It also depends on the mass. So linking back to Newton's second law there, you know, the brakes have a certain force. If you've got a big mass going fast, it's going to take a longer distance to stop. You know, that Humvee on the left there is about 2 tons, 2,000 kilograms. Formula One car, I don't know the exact numbers, is more like 300 kilograms or something like that. And in fact, you can lift the front of a Formula One car up with your hands normally, because the weight of the engine's in the back. Of course, the braking distance is affected by road conditions, more than you imagine. It worries me a little bit here in Doha when it rains and I see how fast people drive. I don't think they sometimes realise how much longer it takes to stop on a wet road. And of course, the condition of the tyres. You know, it's why in most countries there are laws that say you have to have a certain depth of tread on your tyres, and a tyre like that would normally be illegal. So there's typical slotting distances. You can see that they increase quite a lot with speed, and that's to do with the kinetic energy of the car. If you remember, if you double the speed of the car, oh no, we're going to find out, yeah, it actually quadruples the kinetic energy. Okay, and finally in this topic, looking at forces, we looked at Hooke's law. If you remember, we did an experiment, okay, we put masses on a spring and measured the length of the spring and how far it had stretched, the extension. And when we did a graph of this, the first part of the graph is a straight line. And that part of the straight line is what we call Hooke's law. And in maths, we say the extension of the spring, how far the spring is stretched, is proportional to the force applied. That means it's a straight line. That's what proportional means, basically. That happens until we get to that limit of proportionality. After that, if you remember, the spring doesn't go back to its original position. You've basically broken the spring. Okay, so that's Hooke's laws in words. This one you do need to know. A material is said to obey Hooke's law if the extension, how far it's stretched, is directly proportional. In mathematics, if it's a straight line going through 0, 0, we say it is directly proportional to the applied force, the force you put on the spring. You know, many materials obey Hooke's law, even if it's just for a small portion. So even steel, when you apply a force to it, it will stretch and go back to its original shape. Obviously, you need a very big force. But if you think about it, that makes sense, because a spring is steel, isn't it? Glass, even wood, to a very small extent, will obey this. Some materials, rubber being an example, does not obey Hooke's law. So the graph of force against extension is always a curve. I think that is it. Okay, so that was topic 1, forces of motion. If I was you, I'd go through the PowerPoint again, make some notes, look at the notes in your books, then go online and look up IGCSE forces of motion, IGCSE past paper questions. Have a go at some questions. It's the best way to study. Okay.